Have you ever found yourself just guessing? You know, writing code, running it, seeing if it works, and then tweaking it over and over again? Well, if that sounds familiar, you're in the right place. Today, we're throwing that whole process out the window. We're not just going to be coders, we're going to be detectives. We're going to learn how to solve problems with pure logic and solid proof before we even think about writing a single line of code.
And that, right there, is our guiding principle. Think of it this way. Every problem is a crime scene. And instead of jumping to conclusions or trying random things, we're going to do what a real detective does. We're going to follow the evidence, identify the hard constraints, and logically deduce the only possible solution. So let's open up our first case file, the two-sum problem. Now, on the surface, it sounds pretty straightforward, right? You've got a list of numbers, you've got a target number, and you just have to find the two numbers in that list that add up to it. But like any good mystery, the real story, well, that's hidden in the details. All right, first things first. Every detective starts by surveying the crime scene. For us, that means we need to analyze what we call the problem space, basically the environment where all our clues exist. We have to ask ourselves, what are we really working with here? Okay, here are the facts of the case. Our input is an array of integers. So it's a sequence, and every number has an index, a specific location. This is our first major clue. It tells us we can go through it one item at a time, sequentially. But this simple structure, it's hiding a critical weakness, a flaw that is going to define our entire investigation.
And here it is. This is the smoking gun. If we want to find a number in this array, we have no choice but to scan through it, which is incredibly slow. We can't just ask, hey, is the number 7 in here, and get an instant yes or no. This single constraint is, without a doubt, the most important clue we have, because it absolutely forces us to look for an outside tool. The array alone just won't cut it.
And that realization leads us to something we call the transit control system. Now, this is a core principle for us detectives. The constraints of the problem don't just suggest our tools, they demand them. We don't get to just pick our favorite data structure. The clues themselves tell us exactly what we need to crack the case. So let's think about this logically. How are we going to navigate through our list of numbers? Well, we could use nested loops, but that's way too slow. It violates our need for efficiency. We're not dealing with a graph, so those methods are out. By pure process of elimination, a single linear scan is the only logical path forward. You see, it's not a choice we make, it's a conclusion we reach. And what about that massive lookup problem we found? We need a way to instantly check if we've seen a number before. Think of it like a detective's ledger or a dictionary. You don't read the whole book to find one word, you just flip right to it. That's constant time lookup. The array can't do that. A set is fast, yeah, but it throws away the indices, which we need for our answer. So again, through pure deduction, only one tool fits the bill, the hash map. It gives us that lightning-fast lookup, and it remembers the index. It is the only choice. Let's just let that sink in for a second. The correct tool isn't something you just pick out of a toolbox because you like it. The correct tool is the only one left after the problem's own constraints have eliminated everything else. The solution is derived, it's not invented. Okay, we have our navigation strategy and our essential tool. But hold on. We are not writing any code yet. No way. A real detective proves their theory before they make the arrest. For us, this is the most important step, the pre-transcription validation. This is our proof. And this, right here, is the question that separates the amateurs from the pros. How can we be 100% certain this whole plan is going to work? The answer is we build a proof layer. Let's walk through exactly how to do that. This table, this is our proof in action. So imagine our hash map is a detective's notebook. We'll call it the recorder. Okay, let's start. We're at index 0. The number, our candidate, is 2. To get to our target of 9, we need its partner, its complement, which is 7. We check our recorder. Is 7 in there? Nope, it's empty. So we make a note. We saw the number 2 at index 0. And we move on. Next, we're at index 1. The candidate is 7. Its complement is 2. We check the recorder and bingo. There it is. We have seen a 2 before at index 0. The proof is complete. The solution is valid. Case closed. And this is the absolute key insight. This changes everything. We are not blindly searching for an answer. With every single step, we are asking a very precise question. Have I already seen the complement to the number I'm looking at right now? We are verifying a hypothesis. not discovering a solution from scratch. This table proves our logic is completely sound. So, only now, with our airtight proof in hand, do we actually proceed to execution. And at this point, it's not an adventure anymore. It's really just a formality. We're simply walking down the exact path that we've already proven leads to the correct answer. So let's watch this play out frame by frame. There's no mystery left. This is just following the plan. Frame 1, our candidate is 2. We look for its complement, 7. In our recorder, it's empty, not there. So we store 2. Done. Frame 2, our candidate is 7. We look for its complement, 2. We check the recorder. And there it is. We found it. The answer is the current index, 1, and the stored index of our complement, 0. Zero guesswork, 0 surprises.
And what about performance? Was that a surprise we discovered after running the code? Of course not. We knew from the start it would be O(n) time complexity because we logically deduced that a linear scan was our only option. And we knew it would be O(n) space because the hash map was the only tool for the job. You see, complexity isn't something you find out later. It's a direct consequence of the logical decisions you made during the investigation.
You know, this whole detective method, this isn't just a clever trick for solving one problem. It's a completely different framework for building software. It's a more rigorous, more reliable, and frankly, a more professional way to work. Just look at the traditional method. You get requirements, you jump to design, you write a bunch of code, and then you spend what feels like forever debugging your own flawed assumptions. Now, compare that to the correct code framework. We insert one critical step right after requirements, proof. You prove that your logic is sound before you ever design the system or write a line of code. And the main benefit here is just monumental. This approach completely eliminates guesswork. It turns debugging from this massive, soul-crushing part of development into a rare event where you're just fixing a simple typo. You replace hope and guesswork with mathematical certainty. So let's end with this final, powerful principle. The solution to a problem isn't something you stumble upon while your code is running. The solution is something you determine, deduce, and prove before you ever begin. And that is the mark of a true detective and a truly professional developer.